This is the second session of the Restricted Boltzmann machine, RBM. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. In this video, we will look at the learning rule of RBM and compare it to that of Boltzmann machine. Next, let's look at the Contrastive Divergence algorithm. And let's look at a deep belief network, DBN, composed of multiple RBMs. Finally, let's implement an RBM model in code. Now let's derive the learning rule for RBM. The energy function and Boltzmann distribution of a restricted Boltzmann machine are as follows. We define the log likelihood function as follows. Here, n is the number of training data points. The v of n is the nth training data point to be input into the visible layer. Then we can update the weights by the following gradient ascent method. If we plug the energy into this equation, P of V can be written like this. Since the BTV is independent of H, it can be moved outside this sigma notation. As we saw in the previous video, this can be written as follows. This vector expression can be written in scalar form as follows. We assume that there are only 3 neurons in the visible layer and only 2 neurons in the hidden layer. For all possible values of h, we add up all these exponential terms. Since we are dealing with a binary restricted Boltzmann machine, each h is either 0 or 1. When h1 is 0, h2 can be 0 or 1. And even when h1 is 1, h2 can be 0 or 1. So this can be expressed using double sigma notation as follows. The following steps were covered in detail in the previous video, so I won't go into them here. Then, this expression can be written as follows. Here, this expression is also called free energy, negative F of V. Using the free energy, P of V can also be written like this. Taking logarithms of both sides of this equation, the log P of V can be written as follows. Now let's find the gradient of L with respect to Wij. To simplify the problem, let's find the gradient of L with respect to W21. We find the partial derivative of log P of V. Differentiate each term of log P of V individually with respect to W21 as follows. This term can be expressed as follows. The first term is when k is 1. The second term is when k is 2, etc. W.1 is the first column vector of the weight matrix, and W.2 is the second column vector. Since W21 belongs to the first column vector, we only need to differentiate the first term. The V to be multiplied by W21 is V2. So if we differentiate the first term, we get this result. This is the conditional probability of H1 being 1 given via n that we derived in the previous video. So this can be written as follows. Next, let's differentiate the second term, log z, with respect to W21. Z Zeta is a normalization factor for computing P of V and is defined as follows. If we plug the energy E into this equation, Z can be written like this. We add up all the exponential negative energies for all possible values of V and H. Here, V is not the training data, but all possible values needed to compute Z. If we reorganize this using this expression as we did in the previous slide, we get the followings. And if we differentiate Z with respect to W21, we get this. Here this is Z times P of V. And this is the conditional probability of H1 being 1 given V times V2. So if we differentiate log Z with respect to W21, we get this. Again, V2 is not the training data, but the values of the second neuron in the visible layer for all possible V. In the next slide, we'll look at how to obtain the V2 via contrastive divergence. Finally, the gradient of L with respect to W21 can be expressed as follows. Similarly, the gradients of L with respect to biases B and C can be easily found as follows. I will skip explaining this. Now that we know the gradients of L, we can use gradient ascent to update each parameter as follows. Next, let's look at contrastive divergence. In this equation, the VIN in the first term represents the ith feature value of the nth training data point, while the VI in the second term represents the state of the ith neuron for one of the possible values of V. There are too many possible cases for V to compute the second term. For example, if V has 10 features, the number of possible cases for V is 1024. But if V has 20 features, this number increases exponentially to about 1,000,000. If V has 100 features, the number of possible cases for V is nearly infinite, making it impossible to compute. To solve this problem, Geoffrey Hinton proposed the contrastive divergence method in 2002. This allows us to approximate the second term. The contrastive divergence algorithm is as follows. We feed the nth training data point Vn to this network, and we estimate Hj by sampling from this probability distribution. If the probabilities for J being 1 and 2 are for 0.9, 0.3, then the vector H is likely to be 1, 0. Then using this H, we estimate the next V by sampling from this probability distribution. Repeat this K times. Then we can obtain the final VI at the kth step. This is to reconstruct the input data V using this model. And typically the number of repetitions, K, is 1. This works well in practice. We use these values for the V and VI in this equation. Then the average can also be approximately expressed like this. Let Hj of x be the probability that Hj becomes 1 given x. Then the equations on the left can be expressed as follows. This equation can be expressed using expectation notation as follows. The first term is the expectation using the training data. And the second term is the expectation using the estimates from the model. So it can be expressed as follows. This is identical in form to the learning rule of a Boltzmann machine. Similarly, the gradients of bias B and C can be expressed as follows. This is the learning rule for a restricted Boltzmann machine using the contrastive divergence algorithm. Next, let's take a brief look at the deep belief network, DBN. A deep belief network is a type of deep learning network formed by stacking multiple restricted Boltzmann machines. Like RBM, it was also introduced by Geoffrey Hinton in 2006. In terms of network structure, a DBN is identical to a multilayer perceptron, MLP. Typically, a DBN is trained as follows. The first RBM is trained to reconstruct the input data. The hidden layer of the first RBM is treated as the visible layer of the second RBM. And the second RBM is trained using the output of the first RBM. This process is repeated until all layers of the network are trained. DBN can be used to pre-train networks for supervised learning that perform tasks such as classification. The purpose of the pre-training is to initialize the weights of the DBN so that they directly represent the input data. In this stage, each RBM module is independently trained via unsupervised learning. Once pre-training is complete and the model's weights are properly initialized, they are further fine-tuned for downstream tasks such as classification. Fine-tuning is performed using labeled data and supervised learning algorithms such as backpropagation. This allows you to train models and improve their performance for a variety of tasks such as classification and regression. The figure on the right is an example of a DBN that performs multi-class classification. Finally, let's implement an RBM model that can reconstruct corrupted MNIST images. Load the MNIST dataset. We will only use 100 images. The pixel values of each image pattern are between 0 and 1. Convert them to binary values 1 or 0. N is 100, the number of input patterns, and M is 784, which is the number of features, that is, the number of neurons in the visible layer. The number of neurons in the hidden layer is set to 500. The learning rate is set to 0.01, and a one-step contrastive divergence algorithm is used. Write a function that samples hidden vectors h from the conditional probability p using the NumPy's random binomial function. If p is 0.9.2, then the probability of h1 being 1 given v is 0.9. And the probability of h2 being 1 given v is 0.2. Then h is likely to be 1, 0. Initialize the model parameters. The number of iterations is set to 2000, and the mini batch size of data is set to 20. Yield a mini batch of training data. Starting with this batch of data, we run the k-steps contrastive divergence algorithm. Here, a one-step contrast divergence is performed, since CDK is set to 1. This gives us V, a reconstructed version of the batch data. Next, we compute E-data and E-model of this formula. When computing E-data, batch data is used, and when computing E-model, the reconstructed V is used. Next, we update each parameter using gradient ascent as follows. And then we compute and save the change in loss. Loss is defined as the mean square of the difference between the batch data and the reconstructed data. Once training is complete, we plot the changes in loss. The changes in loss are as follows. We can see that the loss decreases as the parameters are updated. This means that the input data and the reconstructed data become more and more similar. Write a function that reconstructs the input data x. The input data x is a corrupted image. We input a data point x into the model and get the reconstructed V. Plot the corrupted image and plot the reconstructed image. Next, we write a function that generates a corrupted image pattern. This will erase part of the bottom of the MNIST image like this. Finally, we reconstruct the 10 image patterns. The results are as follows. You can see that the corrupted images have been successfully reconstructed. Let's run this code. We got the following results. So far, we have looked at restricted Boltzmann machines in 2 videos. In the next video, we will look at contrastive Hebbian learning.